Deep beneath the Swiss countryside, scientists have just demonstrated that two disconnected particles can share an identical fate, registering a statistical certainty 5 times past the threshold of random chance. Today, we take you inside the legendary laboratory, where protons collided 1,000,000 times. Antimatter's gravitational pull was finally measured, and researchers were forced to question whether reality possesses any fixed state at all. From quarks reacting faster than light can travel, to antimatter finally revealing its gravitational direction, these discoveries are so bizarre that even the physicists who uncovered them initially doubted their own data. If your mind is already racing, hit subscribe. Get comfortable as we dive into a journey that defies everything we know about physics. Imagine a place where the universe's oldest secrets are being dragged into light, and it's not in a telescope pointed at distant galaxies. It's buried underground, in a ring of metal and magnets so powerful it could bend the very fabric of space around it. For decades, scientists have been smashing the building blocks of existence together at speeds that defy imagination, and what they're finding is making the ground beneath our feet feel a lot less solid than it used to. Let's start with something that sounds like it belongs in a science fiction novel, but it's real, measured, and verified. Imagine you have 2 dice. You roll one in Geneva and someone else rolls the other in Tokyo. Every single time, without fail, they land on the same number. Not sometimes, not most of the time. Every time. And there's no radio signal, no hidden wire, no trick. They just match, instantly, across thousands of miles. That's not magic. That's quantum entanglement. And it's happening inside the Large Hadron Collider, with particles so heavy and so short-lived that they barely exist before they're gone. The particle in question is called the top quark. It's the heaviest fundamental particle we've ever discovered, weighing about as much as an entire gold atom, even though it's far smaller than a single proton. It lives for less than a trillionth of a second before it decays into a shower of lighter particles. You can't see it, you can't photograph it, you can't touch it, but you can measure what it leaves behind. And that's exactly what scientists at CERN did. When 2 protons collide at nearly the speed of light, the energy of that crash can briefly recreate conditions from a fraction of a second after the Big Bang. In that flash of extreme violence, a top quark and its antimatter twin, an anti-top quark, are born together. They fly apart in opposite directions, sometimes at nearly the speed of light. And here's where things get strange. These 2 particles have a property called spin. It's not spin like a top spinning on a table, it's more like a built-in direction. A hidden compass needle baked into the particle itself. Under normal physics, you'd expect each particle's spin to be fixed the moment it's created, independent and separate, like 2 coins that were already flipped before they left the slingshot. But that's not what the data showed. Instead, the 2 particles behaved as if their spins were still connected after they separated, linked together no matter how far apart they traveled. Measure one, and the other instantly matches it every time, as if they were still one object split into 2. This is quantum entanglement, and it's been observed before, but almost always with small, gentle particles, like photons drifting quietly through a lab, cooled and shielded from any outside disturbance. Nobody had confirmed it inside something as violent as a proton collision, where energy levels are billions of times higher and the particles crash apart in total chaos. One scientist compared trying to detect this signal inside the collider to hearing a single whisper at a rock concert packed floor to ceiling. The noise around it is enormous. Finding the whisper and proving it was real and not random background noise took analyzing about 1 million pairs of these particles. When the team finished, the result blew straight past the bar for a discovery, landing at more than 5 standard deviations from random chance. In physics, that number is the gold standard. It means the odds of this happening by accident are smaller than 1 in a million. For the first time, entanglement had been caught in the most extreme, most energetic environment humans have ever created. The heaviest particle in existence had just shown scientists that its fate was tied to its twin instantly, with no visible connection between them. But a strange link between two particles is only the beginning. What that link actually means is the deeper mystery, one that terrified physicists for almost a century before anyone dared to test it this way. Picture you and a friend each grab a glove from a pair without looking inside the box. You fly to opposite sides of the planet, then open your glove at the exact same moment. The instant you see a left glove, you know with zero doubt that your friend is holding the right one. No signal traveled between you. You just knew because the pair was linked from the start, decided the moment the gloves were packed. That's the simple version of entanglement. And for a long time, many scientists believed it worked exactly like the glove example. Each particle secretly carried its final answer the whole time, hidden inside it, waiting to be revealed. Nothing mysterious, just information we couldn't see yet, tucked away like a sealed envelope, waiting to be opened. Albert Einstein hated the alternative explanation. Some physicists claim the particles did not have a fixed answer at all until the moment someone measured them. Before that moment, both outcomes existed at once, like a coin balanced perfectly on its edge. The act of measuring one particle was what forced an answer to appear, instantly, for both particles, no matter how far apart they were. Einstein called this idea spooky action at a distance, a phrase that stuck for decades. To him, it broke one of the most basic rules of the universe. Nothing can travel faster than light, and information should not be able to leap across space with zero delay. He believed a hidden explanation had to exist, some deeper layer of reality that would make the spookiness disappear once we understood it fully. For decades, nobody could actually test which idea was correct, until a physicist named John Bell, who later worked at CERN, designed a clever mathematical way to check. He built something now called Bell's inequality, a rule that hidden, pre-decided answers would have to follow if Einstein was right. If entangled particles ever broke that rule, it would mean there was no hidden answer at all. It would mean reality really does stay undecided until the moment someone looks. In the 1970s and 1980s, scientists began running real experiments to test this. Photons sent across a lab broke Bell's rule again and again, in setup after setup, closing off loophole after loophole. In 2022, 3 physicists won the Nobel Prize in Physics for proving this beyond doubt using careful, controlled setups with gentle particles. But those experiments all shared one thing in common. They happened in calm, quiet conditions, nothing like the chaos inside a particle collider. Some scientists assumed entanglement might simply not survive an environment that violent. Too much noise, too much energy, too much chaos for something this delicate to hold together. That assumption is exactly what the top quark experiment just shattered. Entanglement did not fade in the chaos. It survived a crash so violent it briefly recreated conditions from the early universe, and it still held. Einstein spent years hoping this idea was wrong. CERN just tested it at the highest energy scale ever attempted, and reality sided against him. But to understand why that result was so hard to trust at first, you have to understand exactly how impossible this measurement seemed before anyone tried it. When a physicist first suggested searching for entanglement inside the world's most powerful particle collider, other scientists were skeptical. It sounded like trying to hear a pin drop during a fireworks show. The collider was not built for delicate quantum measurements. It was built to smash things together as hard as possible and sort through the wreckage. One of the physicists behind the idea later admitted it took real effort just to convince other scientists the project was worth attempting. Entanglement was already proven. Physicists had tested it for decades. Why spend years chasing it again inside the messiest, highest energy environment available, where the odds of success looked slim? The answer came down to one simple gap in human knowledge. Every previous test of entanglement happened at low energy, with gentle particles like photons that barely interact with anything around them. Nobody had confirmed whether entanglement still held up at extreme energy, inside violent collisions involving some of the heaviest particles that exist. It was an assumption, not a fact. And in science, an untested assumption is exactly the kind of thing that eventually breaks. To even attempt the measurement, the team needed a completely new method. Top quarks do not sit still long enough to observe directly. They vanish in a fraction of a trillionth of a second, decaying into a shower of lighter particles that fly off in different directions. Scientists cannot watch the top quarks spin. They can only reconstruct it, like detectives piecing together a crime scene from scattered clues left behind. The clue they focused on was the angle between two particles created when the top quark and its twin decayed. By carefully measuring that angle over and over across roughly 1 million collision events, they could indirectly calculate whether the original pair's spins had stayed linked. It's a little like trying to prove two people were dancing perfectly in sync using only photographs taken after they had already left the dance floor and gone their separate ways. You cannot see the dance directly. You have to work backward from the footprints they left behind. The team also had to rule out every other explanation: random chance, errors in their detectors, quirks in the simulation software used to model particle collisions. Each possibility had to be checked and eliminated before anyone could trust the result. This is why the discovery took years, not days. Scientists are trained to be suspicious of their own exciting results. An extraordinary claim, especially one this strange, demands extraordinary proof before anyone announces it to the world. When the proof finally arrived, it did not creep past the finish line. It crossed the threshold for a confirmed discovery by a wide margin, verified independently by two separate detector teams working at CERN, using different equipment and different analysis methods. Two competing teams checking each other's work without even planning to, both landed on the same impossible answer. That kind of agreement is rare, and it is exactly what turns a strange result into a confirmed law of nature. But even once the entanglement result was locked in, an even stranger question was already forming in the room. If particles stay linked at these energies, what else might be linked that we have not thought to check? To understand exactly how confident scientists became in this result, picture flipping a simple coin. If you flip it 10 times and get heads every time, that could be luck. If you flip it 1 million times and it lands heads every single time, luck stops being a believable answer. Something is actually connecting the outcome. That is roughly the scale of what the Atlas team actually analyzed at CERN. Around 1 million pairs of top quarks and their antimatter twins, each one created and destroyed in less time than light takes to cross a single atom. Out of that mountain of data, they needed to isolate one extremely specific signal buried inside a sea of ordinary particle debris that had nothing to do with entanglement at all. The equivalent of finding one true clue tucked inside a mountain of false leads. Think of it like searching for a single specific grain of colored sand scattered across an entire beach, except the beach refreshes itself billions of times a second, and you only get to look at each grain once before it disappears forever, never to be seen again. The particles most likely to show the entanglement signal came from a very specific energy level, right around the minimum amount of energy needed to produce a top quark pair in the first place. At that narrow energy range, the two particles are born closest together, moving slowest relative to each other, giving their linked spins the best chance of being detected clearly. Outside that narrow window, the signal grew weaker and harder to separate from noise, so scientists had to be precise, filtering their enormous dataset down to the exact conditions where entanglement would be easiest to confirm, without cherry-picking results in a way that would bias the outcome or quietly favor the answer they hoped to find. Every step of this process had to be checked carefully against something called a null hypothesis, which is really just a fancy formal way of asking one honest question. What would this data look like if entanglement was not real at all? If the answer to that question matched what they actually saw, the discovery would fall apart. It did not fall apart. The pattern they found matched what entanglement should look like, and it did not match what random disconnected particles would produce. The gap between the two possibilities was large enough to convince skeptical physicists across the entire field. The kind of gap that leaves almost no room for a different explanation. This is also where this particular story becomes bigger than just one single experiment happening in one single lab. If entangled behavior can survive being created inside the most violent energetic collisions humans can produce, then entanglement may not be a fragile, delicate phenomenon that only works in gentle laboratory conditions. It may be a fundamental thread woven into particles, no matter how extreme their environment becomes. That idea alone reshapes how physicists think about the universe at its smallest scale. But CERN was not finished. While one team chased the mystery of entangled matter, another was quietly chasing something even stranger. Matter's missing twin. The substance that should have destroyed our entire universe the moment it was born. Every piece of matter in existence has an opposite version of itself called antimatter. An electron has a positive twin called a positron, its exact mirror image. A proton has a negative twin called an antiproton. On paper, antimatter looks almost identical to normal matter, just flipped like a photographic negative. Same mass, same basic behavior, only the electric charge reversed. Here is the genuinely terrifying part of the story. When matter and antimatter touch, they annihilate each other completely, converting their entire mass into a burst of pure energy. Something far more total than any ordinary explosion. Every particle of matter that meets its antimatter twin simply ceases to exist. And so does the twin, both converted instantly into light. According to the best equations in physics, the Big Bang should have created matter and antimatter in exactly equal amounts. Picture a perfectly balanced scale. One side matter, one side antimatter, both filling up at the identical rate as the universe exploded into existence. One particle for every particle. If that balance had held, the story of the universe should have ended almost as soon as it began. Matter and antimatter would have found each other and annihilated completely, leaving behind nothing but a faint bath of light and empty space. No stars, no planets, no you. Obviously, that is not what happened. You are here, reading or listening to this right now. Stars exist. Planets exist. Somehow, in that first fraction of a second, something tipped the scale, even slightly, in favor of matter. For every billion pairs of matter and antimatter that destroyed each other, one extra particle of matter was left standing, with nothing left to annihilate it. That tiny, razor-thin leftover imbalance is the only reason anything exists at all, anywhere in the universe. Every atom in your body, every star in the sky, every planet in the solar system, all of it is made from that narrow margin of surviving matter. The tiny fraction that antimatter failed to erase. Physicists have a name for this mystery: baryon asymmetry, the unexplained imbalance between matter and antimatter. It is one of the biggest unanswered questions in all of science, because nothing in the standard model fully explains why that tip in the scale happened in the first place. It sits quietly underneath every star chart, every physics textbook, every mission humanity has ever sent into space, an open question waiting behind the scenery of everyday reality. To search for answers, scientists at CERN do something almost unbelievable. They manufacture antimatter atom by atom inside one of the only facilities on Earth built to create and trap it safely. It is slow, expensive, and dangerous to the equipment, because a single moment of contact with normal matter destroys what took enormous effort to build. And once you have antimatter in hand, an even bigger question appears. Does it behave exactly like normal matter in every way? Or does it hide a secret difference? Something that could finally explain why matter won the battle at the birth of the universe. To answer that, scientists needed to test one of the most basic forces there is, gravity, on a substance nobody had ever been able to drop and watch fall. Drop a ball from your hand, and it falls. Every object you have ever seen behaves this way without exception. But scientists had never actually confirmed that antimatter falls the same way, because antimatter destroys itself the instant it touches any container built from normal matter. Every scale, every cup, every tabletop in the world is made of ordinary matter, which makes even the simplest measurement almost impossible to attempt. Imagine trying to study a single raindrop by catching it in your bare hand, except the instant your skin touches the water, both your hand and the raindrop disappear completely, gone without a trace. That is the basic problem scientists faced for decades. You cannot drop antimatter into a normal cup, a normal tube, or a normal scale. Contact means destruction. At CERN's antimatter factory, scientists solved this with an idea that sounds almost impossible. They built a trap made entirely of magnetic fields, an invisible cage with no physical walls at all, holding its prisoner without ever touching it. Anti-hydrogen atoms, the antimatter version of hydrogen, float suspended inside this magnetic bottle, never touching any solid surface, held in place purely by invisible force. Building this trap, called alpha-G, took years of careful engineering. Every part of the setup had to be adjusted with extreme precision. Even the smallest flaw in the magnetic field could let the antimatter drift sideways and touch a wall, destroying the experiment before any measurement could happen. Every wire, every coil, every piece of equipment surrounding the trap had to be checked and rechecked before a single anti-hydrogen atom could safely be released inside it. One of the lead scientists later said it took 30 years to reach the point where they could finally make anti-hydrogen hold on to it and control it well enough to drop it in a way that would actually respond to gravity. 30 years for an experiment that on paper sounds as simple as letting go of a ball. Here is why it was so difficult in the first place. Anti-hydrogen atoms are incredibly hard to produce at all. Scientists combine antiprotons with positrons, the antimatter version of electrons, one atom at a time, inside conditions cooled close to absolute zero, the coldest possible temperature in the universe. Then, they must trap those atoms using magnetic fields precise enough to hold something invisible, weightless to the touch, and instantly destructive on contact. Once enough anti-hydrogen atoms were finally trapped inside the vertical chamber, after years of preparation, the team designed the actual test. They would slowly relax the magnetic field, opening the trap just enough to let gravity and only gravity decide which way the atoms drifted. If gravity pulled them down, more atoms should exit through the bottom of the chamber. If gravity somehow pushed them up, or if antimatter had no reaction to gravity at all, the atoms should exit evenly from top and bottom, or even drift upward instead. This was the moment 30 years of preparation had been building toward, a machine holding nothing but empty space and magnetic force, about to answer a question humans had wondered about since the moment antimatter was first discovered in a laboratory. When you finally let it go, which way does it fall? Picture a tall, narrow glass tube, roughly the height of a school bus standing straight up on its end. Inside it, invisible magnetic walls hold a small cloud of anti-hydrogen atoms suspended in the middle, neither touching the top nor the bottom. This is the moment the Alpha-G team had been preparing for across 3 decades of work. The payoff of every year spent perfecting the trap. Slowly, carefully, the scientists began weakening the invisible magnetic trap. As the invisible walls relaxed, the anti-hydrogen atoms were free to drift, pulled only by whatever forces acted on them naturally. If normal gravity applied to antimatter exactly the way it applies to everything else, the atoms should sink toward the bottom of the chamber, then touch the wall and instantly annihilate in a tiny flash of energy. Each of those flashes acted like a tiny, precise signal, marking exactly where an atom had struck the chamber and vanished forever. By tracking hundreds of these flashes across many repeated trials, the team could map out a pattern. More flashes at the bottom would mean gravity pulled the antimatter down. More flashes at the top would mean something had pushed it up instead, a result that would have shattered a basic assumption in physics. When the team carefully averaged their results across 7 separate release trials, the pattern that emerged was unmistakable. The antihydrogen atoms fell downward, annihilating far more often at the bottom of the chamber than at the top. Antimatter responded to gravity almost exactly the way ordinary matter does, accelerating downward at close to the same rate you would expect from a dropped ball on Earth. For most physicists, this was the expected outcome based on decades of indirect evidence and theoretical predictions. But an expected result is not the same thing as a confirmed one. Until this experiment, nobody had ever directly watched individual antimatter atoms fall under gravity and measured it. The result finally closed a genuine gap in scientific knowledge that had existed since antimatter's discovery in the 1930s. It also ruled out one popular, hopeful idea. Some physicists had wondered for years whether anti-gravity might explain the missing antimatter mystery. If antimatter had repelled itself and repelled ordinary matter, gravity could have separated the two substances early in the universe's history, keeping them apart before they had a chance to annihilate each other. That would have explained why so little antimatter remains today. This experiment closed that door. Antimatter does not repel gravity. It falls, just like everything else, pulled toward mass. The same way an apple is pulled toward the ground. The same way a coin dropped off a bridge finds the river below. Whatever caused matter to outnumber antimatter at the birth of the universe, it was not a difference in how gravity treats the two substances. That answer solved one mystery, but it deepened another. If gravity was never the reason antimatter mostly disappeared, then something else tipped that ancient scale in matter's favor, and scientists still do not fully know what that something is. The search for the answer leads back into the collider itself, where physicists are hunting for a much smaller, much stranger kind of imbalance. If matter and antimatter were truly created in perfectly equal amounts, and gravity treats both of them the exact same way, something else had to break the balance. Physicists believe the answer is hiding inside a property called charge parity symmetry, usually shortened to CP symmetry. It is a rule that says the laws of physics should look identical if you swap every particle for its antimatter twin and flip the entire scene like a mirror image. If CP symmetry held perfectly, matter and antimatter would behave in completely identical ways forever, with zero exceptions of any kind. But scientists have found small cracks in that symmetry before. Tiny moments where matter and antimatter do not behave quite the same. These cracks are called CP violation, and they are one of the leading suspects behind why the universe filled up with matter instead of antimatter. Picture two identical twins who are supposed to make every decision the exact same way, down to the smallest detail. Almost all the time they do, but every so often, in a specific rare situation, one twin makes a slightly different choice than the other, just barely enough to notice if you are watching closely. That tiny inconsistency is what physicists are hunting for. Except the twins are matter and antimatter, and the decisions are the results of trillions of particle decays. At CERN, a dedicated experiment called LHCb specializes in exactly this kind of hunt. Its detector is shaped differently than the giant symmetrical Atlas and CMS machines. Built instead like a long, forward-pointing arm, designed specifically to catch particles called quarks the instant they are born and watch them decay. It tracks the split-second differences in how matter versions and antimatter versions of the same particle fall apart. Most of the time, the two decay in matching ways. But researchers have identified specific particles, including certain heavy particles called baryons, where the decay patterns show a measurable, confirmed difference between matter and antimatter behavior. A genuine crack in a symmetry that was supposed to hold perfectly. The differences found so far are small, far too small to fully explain the massive imbalance that left our universe filled with matter and almost no antimatter. This is one of the most frustrating and exciting problems in modern physics. Scientists have proven CP violation exists. They just have not found enough of it yet to solve the whole mystery, leaving a gap between what is proven and what is needed. That gap between proven and enough is exactly why physicists keep returning to the collider year after year, searching for new particles or new decay patterns that could explain the missing piece. Every confirmed asymmetry is treated like a clue at a crime scene, small on its own, but potentially connected to something much bigger once enough of them are gathered together. Some physicists suspect the true answer might not even be fully visible using current technology, that it may require particles or forces the standard model does not yet include. If that is true, discovering the missing piece would prove there are entire categories of physics still waiting to be found, hiding just beyond the edge of what today's most powerful machine can detect. Step back for a moment and look at what these two discoveries actually mean when you put them side by side. Entangled particles that share a fate across any distance, with no visible connection. Antimatter that behaves normally under gravity, ruling out one of the simplest explanations for why the universe is not made of equal parts matter and nothing. Both results point toward the same uncomfortable idea. The universe does not always work the way common sense expects it to. Common sense says objects have fixed properties the whole time, whether or not anyone is looking at them. A ball is round whether your eyes are open or closed. A rock has a location whether or not you check on it. That assumption has guided human thinking for as long as people have studied the natural world. Quantum entanglement breaks that assumption completely. Before scientists measured the top quark spin, the particles did not have a fixed, locked-in answer waiting to be revealed. The measurement itself was part of what determined the outcome. Two particles born together carried an undecided property between them, and the moment one was measured, both outcomes locked into place at once, instantly, no matter the distance separating them. Physicists have specifically tested for the simpler explanation that the particles secretly agreed on an answer ahead of time and just revealed it later, like two friends planning a prank in advance. That explanation failed every test. The particles genuinely behave as if the answer did not exist until the exact moment it was measured. Try picturing it this way. Imagine flipping a coin, but the coin has no side facing up until the instant you glance at it. Before that glance, it is somehow both heads and tails at once, a blur of possibility. Only your act of looking forces it to become one or the other, strange enough for a single coin. Now imagine a second identical coin on the opposite side of the planet that locks into the matching result the instant you look at your coin, with no delay and no signal passing between them. That is not a metaphor stretched for drama. It is close to what the mathematics of entanglement actually describes. And CERN just confirmed it holds true even inside the most violent, high-energy environment ever created in a lab. This idea has a name in physics, quantum indeterminacy, the concept that certain properties simply do not have a fixed value until they are measured. It sits at the foundation of quantum mechanics, and it has survived nearly a century of attempts by brilliant scientists to disprove it, poke holes in it, or explain it away. Every experiment that confirms entanglement adds more weight to an idea that unsettled even the smartest physicists in history. Reality at its smallest scale may not behave like a fixed, solid stage waiting for us to walk across it. It may behave more like something that stays flexible, undecided, right up until the moment we interact with it. And if that is true at the smallest scale, the next question becomes impossible to ignore. Could that same flexibility exist at scales far bigger than a single particle, in ways we have not yet found a way to detect? To understand exactly what scientists measured with the top quarks, it helps to look closer at the mysterious property called spin. It is one of the strangest ideas in physics, and one of the most misunderstood, because the name makes it sound simpler than it actually is. Borrowed from an everyday word that does not fully capture what is really going on. A basketball spinning on a fingertip has a clear, visible physical rotation you can watch happen in real time. Particle spin is not that. A top quark does not physically rotate the way a basketball does. Instead, spin is a fixed quantum property, almost like a built-in direction the particle carries with it, similar to a tiny compass needle pointing a certain way. Except this compass exists at a scale far smaller than an atom, invisible to any microscope ever built. Scientists cannot see this hidden compass directly. A top quark disappears too fast, decaying into other particles in a fraction of a second. So instead, researchers work backward. They study the particles the top quark decays into, especially a lighter particle called a charged lepton, and measure the angle it flies off at. That angle carries a mathematical fingerprint of what the top quark's spin was pointing toward before it vanished. This is where the story becomes almost like solving a locked-room mystery, using only the scattered evidence left behind. Nobody witnessed the top quark spin directly. Scientists reconstructed it by carefully analyzing the pattern of particles it left in its wake, then comparing that pattern against what pure random chance would produce, checking every alternative before trusting the conclusion. When they compared the spin directions of top quark and anti-top quark pairs against each other across roughly 1 million separate collision events, a clear pattern of correlation emerged. The spins were not independent random directions. They lined up with each other in a specific way, matching the exact mathematical signature that entanglement predicts, and clashing with what completely separate, unconnected particles should have produced. Physicists express how strong this correlation is using a single number called d, a compact way of summarizing an absolutely enormous pile of raw data. In this experiment, the measured value of d was strongly negative, and far from zero, exactly the range physicists had predicted would prove entanglement was present. A value at or near zero would have meant no connection at all. The value the team measured left no real room for that interpretation. This single number, extracted carefully from an ocean of raw data, became the anchor of the entire discovery. Every checked possibility, every alternative explanation the team tested, failed to explain a number that far from zero. Only entanglement fit the pattern the data actually showed. It is a strange thought to sit with. A particle too fast to see directly, carrying a hidden compass too small to observe, still left behind enough evidence for scientists to prove it was quietly linked to its twin the entire time. The universe hid its secret in plain sight, buried inside an angle, waiting for someone patient enough to measure it 1,000,000 times over. Science has always had a built-in trust problem. Anyone can announce a groundbreaking discovery. Proving it is real, rather than a mistake, a bias, or a fluke, is the hard part. This is exactly why the entanglement discovery became so convincing so quickly. Two separate teams confirmed it, working with completely separate detectors, separate equipment, and separate analysis methods. The Large Hadron Collider is home to several massive detectors. Each one is essentially a giant camera built to capture the debris from particle collisions. Two of the largest are called Atlas and CMS. Picture them as two enormous stadiums, each packed with sensors, sitting at different points along the 17-mile ring, each independently recording the same collisions from a different angle, using different technology built by entirely separate engineering teams. Atlas published the first full confirmation of entanglement in top quark pairs based on their careful analysis of the angle between decay particles. Independently, the CMS team ran their own investigation using a different experimental approach. Instead of focusing on particles produced near the slowest, closest range, CMS studied top quark pairs moving at high momentum relative to each other. A completely different corner of the data. This second approach mattered enormously to the strength of the result. At high momentum, the two particles separate so quickly that, according to the basic rules of physics, there is not enough time for any signal, even one traveling at the speed of light, to pass between them before they decay. If entanglement still showed up under these conditions, it would rule out any lingering possibility that some hidden, faster-than-light communication was secretly responsible for the result. CMS found the same answer: spin entanglement present and measurable. Even in this stricter test, where classical explanations were completely ruled out by the laws of physics itself, two separate detectors testing two separate corners of the data landed on the exact same conclusion. Two entirely separate competing teams, using two different detectors and two different methods, reached the same impossible conclusion without ever depending on each other's work. In science, this kind of independent agreement carries enormous weight. It means the result is very unlikely to be caused by a flaw specific to one machine, one team, or one analysis choice. This is also why physicists trust this discovery enough to build future research on top of it. A single surprising result might be an error waiting to be found. Two independent surprising results matching each other precisely start to look like a real confirmed feature of the universe. For the scientists involved, this moment represented something bigger than one single experiment. It proved the Large Hadron Collider is far more than a machine for smashing particles apart to see what falls out. It is now officially a tool capable of testing the deepest, strangest laws of quantum mechanics at energy levels nobody thought quantum experiments could survive. That opens an entirely new frontier. If entanglement can be measured this precisely inside a violent particle collision, what other quantum mysteries have been hiding in the wreckage of collisions scientists have already studied, waiting for someone to look at the data in a new way? Once scientists confirmed entanglement was genuinely real inside these collisions, the next question was not whether it existed, but how far it actually went. Entanglement is not an all-or-nothing switch. It has depth, strength, and structure, and physicists have tools to measure exactly how strong and how complex a quantum connection actually is. Almost like measuring the volume of a sound, rather than just noticing it exists. One of these tools is called quantum steering. This is a slightly stronger version of entanglement, where measuring one particle does not just correlate with the other. It actually lets you predict and influence what range of outcomes the second particle can show, almost like gently nudging its possibilities from a distance, without ever touching it directly. Steering had been demonstrated before in gentle laboratory setups, but never confirmed at the extreme energy of a particle collider. Another tool goes even further, called Bell non-locality. This is the strictest possible test available to physicists, the one closest to directly disproving Einstein's hope that hidden, pre-decided answers explain everything. If particles pass this test, it means no ordinary common-sense explanation can account for their behavior. The connection has to be treated as fundamentally quantum, with no simpler explanation hiding underneath. Physicists studying the CERN data found evidence supporting these deeper layers as well, not just basic entanglement, but genuine signs pointing towards steering, and in some analyses, promising hints of full non-locality. Confirming these stronger effects with complete certainty takes more data and more time, and research on this is still ongoing. But the early signs suggest the connection between these particles runs deeper than a simple linked pair. There is also a tool called a steering ellipsoid, a mathematical shape that maps out every possible measurement outcome for an entangled particle. Picture a globe, except instead of representing physical locations, every point on its surface represents a possible measurement result. Before entanglement, this shape would be simple and predictable, close to a perfect sphere. Under strong entanglement, the shape distorts, stretching and shifting in specific patterns that reveal exactly how tightly connected the particles are. Using this method, physicists can measure entanglement almost like measuring the shape of an object with precise geometry, instead of a vague yes or no answer, turning a fuzzy question into a solvable one. This gives scientists an entirely new mathematical language for describing how deeply connected particles are, even inside a collision so energetic it barely resembles anything found in a normal physics lab. Why does this level of detail matter? Quantum entanglement is the foundation behind real, working technology already used today, including quantum computers and highly secure quantum encryption. Understanding exactly how entanglement behaves at extreme energy could eventually influence how future quantum technology is designed, tested, or even protected from outside interference. For now, the discovery stands as proof that the tools built to study gentle, cooled-down quantum systems in a lab can be pointed at the most violent environment humans have ever created and still produce clean, precise, trustworthy answers. That capability alone opens a door physicists are only just beginning to walk through. Antimatter sounds like something pulled straight out of a comic book, but its story in real physics is stranger than fiction. It was predicted first on paper, years before anyone ever detected it in a real experiment, a rare case of mathematics leading the way and reality catching up afterward. In 1928, a physicist named Paul Dirac was working through the mathematics that describe electrons, trying to combine quantum mechanics with Einstein's theory of relativity. His equations kept producing an odd result. For every solution describing a normal electron, there was a second, mirrored solution describing a particle with the exact same mass but the opposite electric charge. Most physicists at the time assumed this second solution was simply a mathematical accident, a strange side effect with no real physical meaning. Dirac disagreed. He suspected his equations were pointing toward the existence of an entirely new kind of particle, one nobody had ever detected, hiding in plain sight inside numbers everyone else had dismissed. 4 years later, in 1932, a physicist named Carl Anderson was studying cosmic rays, high-energy particles raining down from space, using a detector chamber that let him photograph the paths particles took as they passed through. Among his photographs, he found a track that curved exactly like an electron's path, except it curved in the opposite direction. He had found Dirac's predicted particle. Scientists named it the positron, the antimatter twin of the electron, confirmed years after it first appeared as nothing more than a strange line in someone's equations. This single discovery proved something absolutely enormous about the nature of the universe. Antimatter was real, physical, and apparently a fundamental part of how the universe works, not a mathematical accident buried in the equations. If electrons had an antimatter twin, physicists quickly realized every other particle likely had one too. Protons, neutrons, and eventually entire atoms could theoretically have antimatter versions. For decades after this initial discovery, antimatter remained mostly theoretical in practical terms, because creating and studying it required enormous amounts of energy, expensive equipment, and extremely careful, patient handling. Scientists could create antimatter particles briefly inside accelerators, but keeping them intact long enough to study them in detail was nearly impossible, since any contact with ordinary matter destroyed them instantly. Modern facilities like CERN's antimatter factory finally developed the tools needed to slow antimatter particles down, combine them into full antihydrogen atoms, and trap them long enough to run real experiments. What began as an odd, dismissed result buried inside Paul Dirac's equations nearly a century ago has become one of the most carefully studied substances in all of modern physics. This history matters because it shows how often the strangest sounding ideas in physics eventually turn out to be true. Dirac's mathematics predicted something that sounded absurd at the time: a mirror universe of matter hiding inside the equations. Reality confirmed it anyway. That pattern of the math predicting something bizarre and experiments eventually proving it correct is exactly the pattern physicists are chasing again today. As they search for the next hidden particle, the equations are quietly pointing toward. Making even a single antihydrogen atom is one of the hardest technical challenges in all of modern physics, and understanding why reveals just how extreme the entire alpha experiment really is. Every step of the process is fighting against the basic nature of the substance itself, a material that erases itself the instant it makes a mistake. It all starts with antiprotons, the antimatter twin of a normal everyday proton. CERN produces these using a machine called the antiproton decelerator, which sounds backward but makes sense once you understand the problem. Antiprotons created inside the collider move far too fast, and carry far too much energy to be useful for building a stable atom. The decelerator's entire job is slowing them down step by step without letting them touch anything that would destroy them. At the same time, scientists need positrons, the antimatter twin of an electron. These come from a radioactive source and get collected, cooled, and stored using their own separate system, kept completely isolated from ordinary matter until the exact, precise moment they are needed. Once both ingredients are ready, slowed antiprotons and cooled positrons, scientists combine them inside a specialized trap, allowing them to pair up and form full antihydrogen atoms. One antiproton orbited by one positron, the antimatter mirror of a basic hydrogen atom. This process happens inside a chamber cooled to temperatures near absolute zero, colder than deep space itself. Because heat causes particles to move too quickly, to trap successfully, even under perfect conditions. This process is incredibly inefficient, producing even a modest number of antihydrogen atoms that survive long enough to study requires enormous effort, careful timing, patience, and equipment sensitive enough to detect and adjust for the tiniest disturbances. A single stray vibration, a tiny fluctuation in the magnetic field, or the smallest contact with a physical surface can end the experiment early. Once the antihydrogen atoms exist, they must be held in place using alpha G's magnetic trap, an invisible container built entirely from carefully shaped magnetic fields. There are no solid walls anywhere near the antimatter. There cannot be. The entire experiment depends on the atoms never touching a physical surface until the exact controlled moment scientists choose to release them. Every part of this process pushes against the natural tendency of antimatter to destroy itself. The instant conditions are not perfectly controlled. Scientists are keeping a fragile, self-destructive substance alive and stable long enough to ask it a single question. Which way does gravity pull you? It is a bit like building an entire laboratory around a soap bubble, one that pops the instant anything at all brushes against it, and then asking that bubble to answer one of the oldest questions in physics before it disappears. This is why the eventual answer, confirmed after decades of engineering effort, carries so much weight. It is not a quick measurement taken with simple tools. It is the payoff of building, essentially from scratch, one of the only places on Earth capable of holding a piece of the universe's rarest material, still long enough to study it honestly. Before the alpha G results finally came in, there was a real, genuinely serious possibility hanging heavily over the entire experiment. What if antimatter fell upward instead of downward? It sounds like science fiction, but a small number of respected physicists took the idea seriously enough to keep testing for it, publishing careful papers exploring exactly what such a result would mean. If antimatter had repelled gravity, instead of responding to it normally, the consequences would have reached far beyond a single experiment. General relativity, Einstein's theory describing how gravity works, assumes that gravity treats all forms of mass and energy identically. This idea has a name, the weak equivalence principle, and it is one of the most heavily tested, most trusted foundations in all of modern physics. If antimatter had shown even the slightest difference in how gravity affected it, general relativity itself would have needed serious, immediate revision. Every calculation involving gravity, from the orbits of planets to the bending of light around black holes, relies on the assumption that gravity does not play favorites between different types of matter. A confirmed exception would have sent physicists back to rebuild part of that foundation from scratch. There was also a very tempting reason why some physicists secretly hoped this might happen. Anti-gravity and antimatter could have offered a clean, elegant explanation for why the universe contains so little antimatter today. If antimatter naturally repelled itself and repelled normal matter, gravity alone could have pulled the two apart in the earliest moments after the Big Bang, before they had the chance to annihilate each other completely. That single idea could have explained one of the biggest mysteries in physics in one clean stroke. Would have been an exciting, headline-making result, precisely because it broke expectations. Sometimes in science, physicists genuinely hope to find something strange, because a broken assumption often points the way toward deeper, more complete theories, hiding just underneath the current ones, waiting to be uncovered by exactly the kind of result nobody expects. The elegant anti-gravity explanation for the universe's missing antimatter did not survive contact with a real experiment. When the anti-hydrogen atoms were finally released and tracked, they fell downward, matching the predictions of standard gravity almost exactly, closing the door on one of the more hopeful shortcuts physicists had imagined. In some ways, this outcome is less flashy than the alternative would have been. No headlines proclaiming that Einstein was wrong, no dramatic rewrite of general relativity, but confirming an expected result is still real, valuable science. It closes off an entire category of possible explanations, narrowing the search for the true answer to a smaller, more focused set of possibilities. Ruling out anti-gravity does not solve the mystery of the missing antimatter. It just tells scientists clearly where not to look anymore. And in a search this difficult, eliminating a wrong path is sometimes just as valuable as finding the right one, because it means every future experiment can be aimed with a little more precision at the mystery that remains, sharpening the hunt instead of ending it. Sit with this simple thought for just a moment and let it settle in. Every star you have ever seen in the night sky, every planet, every living thing exists because of an imbalance so small it is almost impossible to picture clearly using everyday comparisons. Here is one way to try. Imagine a stadium filled with 1 billion pairs of matter and antimatter particles, all created together at the birth of the universe. Now imagine nearly every single pair finding its opposite twin and annihilating completely, vanishing into pure light. By the end, out of that entire stadium of 1 billion pairs, only one single particle of matter would be left standing. Now picture that same scene repeating in every stadium in every city across the entire early universe, all at once, in the first fraction of a second after everything began. That one leftover particle, multiplied across the entire early universe, is the only reason anything exists today. Every atom in your body traces back to that tiny surviving fraction, the small percentage of matter that never found an antimatter twin to destroy it. The iron in your blood, the calcium in your bones, the carbon holding every cell together, all of it descends from particles that simply got lucky enough to survive the greatest demolition in the history of the universe. If that imbalance had been exactly zero, the universe would have finished annihilating itself within moments of the Big Bang, leaving behind nothing but empty space filled with a faint glow of leftover light. No galaxies, no stars, no chemistry, no biology, just silence stretching on forever, in every direction without end. It is a straightforward conclusion drawn directly from well-tested physics. Scientists can calculate, using confirmed equations, exactly how much matter and antimatter the early universe should have produced, and exactly how completely they should have annihilated each other if the amounts were perfectly equal. The universe we currently live in only makes sense because reality did not follow the simplest, most perfectly balanced outcome. Some rule or process still not fully understood, gave matter a narrow advantage in that first fraction of a second, small enough to almost be a rounding error, but large enough to leave an entire universe standing in its place. This is why physicists treat the search for CP violation and the search for a full explanation of matter and antimatter's imbalance as one of the most urgent, most important open questions in all of science. It is an abstract-sounding topic that reaches far beyond any textbook. It is the reason existence itself was even possible in the first place. The reason there was ever a universe capable of eventually growing stars, planets, and someone curious enough to ask how it all happened. Every experiment at CERN chasing this mystery, From LHCb's detailed particle decay studies to Alpha's antimatter gravity tests, is really chasing the same enormous question from different angles. What tipped the scale that let the universe survive its own birth? Physicists have found small pieces of the answer. The full picture is still missing, and finding it remains one of the biggest unsolved problems modern science has ever faced. The standard model of particle physics has survived more attempts to break it than almost any other single theory in the entire history of science. For decades, experiment after experiment confirmed its predictions with stunning accuracy, correctly forecasting the existence of particles years before technology existed to detect them, sometimes decades before anyone could build a machine powerful enough to check. But a theory that explains almost everything is simply not the same thing at all as a theory that explains absolutely everything without exception. Scientists have known for years that real gaps exist. The standard model cannot explain gravity at the quantum level. It cannot explain dark matter, the invisible substance that makes up roughly 85% of all matter in the universe. It cannot fully explain why matter outnumbers antimatter. And now it faces new pressure from these entanglement and antimatter results, which confirm the theory's predictions, while also highlighting exactly how much remains unexplained underneath them. Think of the standard model like an incredibly detailed, mostly accurate map of a country. It gets almost every road, every city, and every landmark correct. But there are a few regions on the map still marked as blank space. Areas where cartographers know something exists, but do not yet know exactly what it looks like or how large it really is. Every time scientists run a brand new experiment at CERN, they are essentially sending an expedition into one of those blank regions, hoping to sketch in new details. Sometimes the expedition confirms exactly what the map already predicted, strengthening confidence in the existing model. Other times it finds something unexpected, a new landmark that does not fit cleanly onto the current map at all. The entanglement discovery falls into an interesting middle category. It did not contradict the standard model outright. Quantum mechanics, the broader framework that entanglement belongs to, is deeply connected to the standard model already, but confirming entanglement survives at this extreme energy level opens a genuinely new area for exploration. A blank region on the map that nobody had explored with this kind of precision before. Physicists are now asking whether other quantum phenomena, previously only tested in gentle laboratory conditions, might also survive inside violent high-energy collisions. Each one that does adds a new tool for probing the universe's deepest structure, using an energy scale nobody had access to until relatively recently in scientific history. This matters because many physicists believe that whatever eventually explains dark matter, or the true source of the matter and antimatter imbalance, will likely be found hiding somewhere in these same extreme, high-energy conditions. The standard model's blank regions are not scattered randomly. Many of them sit precisely at the energy levels only a machine like the Large Hadron Collider can reach. Every crack these experiments reveal is not a failure. It is a signpost pointing scientists toward exactly where the next major discovery in physics is most likely to be hiding. A marker planted on the edge of the map, showing explorers exactly where to look next. One particular detail about entanglement tends to unsettle people more than any other part of this entire story, and it is worth slowing down to look at directly and carefully. Distance simply does not weaken the connection at all. Not gradually, not eventually, not even a little. With almost every other force or connection in physics, distance matters enormously. Gravity weakens the farther apart two objects are. Light fades and eventually disappears over long enough distances. Sound stops traveling entirely once you get far enough away from its source. Nearly everything we experience follows this same basic pattern. Strong up close, weaker with distance, gone eventually, fading the way a voice fades across a big, empty stadium. Entanglement simply does not follow that pattern at all. In experiments specifically designed to test this, entangled particles have maintained their connection across distances of many miles, with no measurable weakening based on distance whatsoever. The correlation between them, stays exactly as strong at long range as it is at short range, as if the concept of distance simply does not apply to the connection the way it applies to everything else in the universe. This does not mean information travels between entangled particles faster than light. A common misunderstanding worth clearing up. You cannot use entanglement to send a message instantly across the universe, because the actual outcome of each measurement is random. You cannot control what result you get when you measure your particle. So you cannot use it to transmit a chosen message to someone holding the other particle. The connection is real, but it cannot be used to break the universe's speed limit for sending usable information, a limit that still holds firm. Still, the correlation itself, the fact that both particles, results, always match up in a specific, predictable pattern once compared later, appears completely unaffected by the space between them. Some physicists interpret this as evidence that entangled particles are not truly separate objects at all, even when they are physically far apart. In a strange sense, they may be better described as a single connected system that merely appears, to our normal way of thinking about space, like two different things in two different places. This idea connects to a much larger question some physicists have started asking seriously. What if space itself, the very fabric that seems to separate objects and locations, is not the most fundamental layer of reality? A small but growing number of researchers have proposed that space might actually emerge from something deeper, built out of networks of entangled connections between particles, rather than existing as a fixed backdrop that particles simply sit inside the way actors sit on a stage. Under this view, entanglement would not just be a strange side effect happening inside space. It would be part of what constructs space in the first place. It remains a genuinely speculative idea, far from confirmed, and CERN's results do not prove it directly. But every confirmed case of entanglement surviving extreme conditions adds another small piece of evidence that keeps this bold idea alive in serious scientific conversation. Quantum steering, the deeper form of entanglement mentioned earlier in this story, deserves a closer look because it is easier to picture than it sounds. And it hints at something genuinely strange about how connected two particles can actually become, something that goes far beyond a simple matching pair. Imagine two sealed boxes, one given to you, one given to a close friend, on the opposite side of the planet. Inside each box is a ball that can show one of several colors, but the color is not fixed until someone opens the box and looks. In an ordinary, non-quantum world, opening your box would tell you nothing about what color your friend's ball will show. The two boxes are independent, sealed off from each other completely. Quantum steering breaks that ordinary independence in a very specific and measurable way. If your box and your friend's box are entangled through steering, the choices you make about how you look inside your box actually shape the range of possible colors your friend's ball can show before they even open theirs. You are not choosing their outcome directly. You cannot force a specific color to appear, but you are narrowing or steering the range of what becomes possible for them purely through your own actions on your own box. This is a stronger and far more specific claim than basic entanglement, which only says the two results will match up in a pattern once compared later. Steering says something more active is happening. That one particle's treatment genuinely shapes the possibilities available to its distant partner in real time, not just after the fact. Confirming steering requires far more detailed data and stricter mathematical tests than confirming basic entanglement. Because scientists have to rule out even more alternative explanations before they can be confident the effect is real and not some hidden statistical trick buried in the data. Early analysis of the CERN results has shown signs consistent with steering, though researchers are continuing to refine these measurements with additional data as the experiments continue, tightening the case year by year. So why chase something this subtle and this genuinely difficult to confirm? Because steering has real practical value beyond pure curiosity. It plays an important role in quantum cryptography, a method of encrypting information so securely that any attempt to secretly intercept it would disturb the entangled particles and instantly reveal the intrusion. Steering also matters for certain designs of quantum computers, machines that use entangled particles to perform certain calculations far faster than any traditional computer ever could. If steering can eventually be confirmed and controlled at these extreme high-energy scales, it would not just be a scientific curiosity locked away inside a research paper. It could eventually influence how future quantum technology gets designed, tested, and trusted. The line between a strange discovery about the deep nature of reality and a practical tool used in everyday technology has a way of blurring faster than most people expect. And steering sits right on that blurry edge today. There is one more important concept worth understanding clearly, because it sits quietly underneath almost every strange result in this story, and it explains exactly why so many scientists reacted with such disbelief when the data first came in. It is called locality. Locality is the intuitive idea that objects can only be directly influenced by their immediate surroundings. A light switch on one side of your house does not instantly affect a lamp on the opposite side of town. For something to influence something else, some kind of signal, force, or object has to physically travel between them, and that travel takes time. Nothing in the universe, according to Einstein's physics, can carry information faster than the speed of light, the fastest signal allowed anywhere in the cosmos. Locality feels so obviously true that most people never think to question it. It matches everything we experience in daily life. Yet entanglement, tested and confirmed again and again, appears to violate it directly. Two particles separated by enormous distances show correlated results that cannot be explained by any signal traveling between them at or below the speed of light, no matter how the experiment is arranged. Physicists have worked incredibly hard for decades to close every possible loophole in these experiments, specifically to check whether some hidden undetected signal might secretly explain the correlation without truly breaking locality. These are called loophole-free tests, and they have been performed successfully using photons in careful laboratory conditions, ruling out these hidden explanations with extremely high confidence. The CERN result adds something genuinely new to this conversation. In the CMS experiment, top quark pairs were specifically studied at high momentum, the exact condition where the particles separate from each other so quickly that even a signal moving at the speed of light would not have enough time to travel between them before they each individually decay. Under these conditions, classical signaling is not just unlikely, it is physically ruled out by the numbers involved. And even under this strict condition, entanglement still held. The correlation still appeared exactly where relativity itself guarantees no ordinary signal could have caused it, in a window of time too short for any known force to bridge. This does not mean physics itself is broken, or that faster-than-light communication has somehow finally been discovered. Locality in the classical sense genuinely does appear to fail at the quantum level, but not in a way that lets anyone send a message faster than light or violate causality. The two ideas, quantum non-locality and relativity, currently coexist without directly contradicting each other, even though physicists still do not have a fully satisfying intuitive explanation for why both can be true at once. That unresolved tension between two of the most well-tested ideas in all of physics is exactly the kind of gap where major future discoveries tend to hide. CERN's newest results have not closed that gap. They have pushed it into a more extreme, higher energy environment than anyone had tested it in before, and the gap held firm. Behind the mathematics used to prove entanglement lies the story of one quiet physicist who spent much of his career at CERN, largely working on completely different projects while quietly developing one of the most important ideas in the history of quantum physics as something closer to a personal side project. John Bell was a theoretical physicist from Northern Ireland who joined CERN in the late 1950s. His main job involved practical work related to particle accelerator design. Useful and respected, but not the kind of work that makes headlines. In his spare time, away from his official responsibilities, Bell kept returning to a question that had bothered him for years. The same question that had bothered Einstein decades earlier. Was entanglement truly as strange as quantum mechanics claimed? Or was there a simpler, hidden explanation nobody had proven wrong yet? He carried that question with him for years, working through it quietly alongside his official duties. In 1964, Bell published a short paper containing what became known as Bell's inequality, a precise mathematical test that could finally settle the question experimentally rather than through endless debate and philosophy alone. His work laid out exactly what results a hidden, pre-decided explanation would have to produce, and showed that true quantum entanglement should be able to break that limit under the right conditions. At the time, Bell's short paper attracted surprisingly little attention from the wider physics community. Testing his idea required experimental techniques that did not yet fully exist. For nearly 2 decades, the paper sat as an interesting theoretical possibility, waiting for technology to catch up to the question it asked. By the 1980s, physicists finally built experiments precise enough to test Bell's inequality directly using pairs of entangled photons. The results broke Bell's limit clearly and repeatedly, exactly as true quantum entanglement predicted, over and over in lab after lab. Hidden, pre-decided explanations could no longer account for what experiments were showing. This work eventually helped earn 3 physicists the Nobel Prize in Physics in 2022, decades after Bell first published his idea. And sadly, years after Bell himself had passed away in 1990. There is something fitting about the fact that CERN, the very same institution where Bell quietly developed his groundbreaking idea as an outsider project alongside his main job, is now the place where his old test has finally been pushed to the most extreme energy scale ever attempted. The top quark entanglement result did not just confirm quantum mechanics again in a general sense. It extended Bell's original question into completely new territory, asking whether his decades-old test would still hold true inside the most violent particle collisions humans have ever produced. It did. A question first written down by one physicist working almost alone, using nothing but pen, paper, and careful reasoning, has now been tested and confirmed inside the most powerful and complex machine ever built by human beings. Few ideas in the history of physics have traveled that far, from a quiet side project to a confirmed law, tested at the extreme edge of what technology allows. There is a comforting old idea in classical physics called realism. And understanding exactly what it claims makes it easier to understand exactly what these experiments threaten to take away. The quiet assumption sitting underneath almost every intuition we naturally have about the world. Realism, in this specific context, is the belief that objects have definite, fixed properties at all times, whether or not anyone is measuring or observing them. A rock sitting alone on a mountain still has a specific size, shape, and location, even if no human eye or instrument ever checks on it. This assumption feels so obviously true that most people never think of it as an assumption at all. It simply feels like common sense. Quantum mechanics, and specifically the strong entanglement results just confirmed at CERN, directly challenge this comforting picture of the world. The measurements taken on the top quark pairs are not consistent with the idea that each particle already had a fixed, hidden spin value the entire time, quietly waiting to be revealed. The particles behaved as though their properties genuinely remained undetermined until the moment of measurement, exactly as the stricter, less comforting version of quantum theory predicts. This does not mean nothing is real, or that reality somehow does not exist without an observer. An idea that gets exaggerated and badly misrepresented constantly in casual conversation. It means something more precise and, in some ways, stranger. Certain specific properties of certain specific particles do not appear to have single fixed values until a measurement forces one to appear. The particle is real. Its exact spin value before measurement simply was not fixed yet. Still open, still waiting. Physicists sometimes describe this using the idea of superposition, a term for a particle existing across multiple possible states simultaneously until measurement collapses that range of possibilities down into one single definite outcome. It sounds abstract, but it has been tested and confirmed across thousands of experiments over the past century, using many different types of particles and increasingly extreme conditions, now including the violent environment inside a particle collider, a setting nobody expected such a delicate effect to survive. Some physicists have proposed alternative interpretations that try to preserve a version of realism, arguing that the particles do have fixed values, but that our universe is somehow connected to countless other parallel versions of itself where every possible outcome happens simultaneously. These ideas remain deeply debated, difficult to test directly, and far from settled science. What is settled is the data itself. The correlations exist. The predictions of standard quantum mechanics match what was observed. The explanations underneath those correlations remain an open, actively debated question. What CERN's results do not do is offer a tidy, comfortable resolution to this century-old debate. They simply add more weight to the side that Einstein originally resisted, confirming it now at an energy scale nobody had access to when the argument first began. The debate over what reality truly is underneath the equations remains wide open, even as the experimental evidence keeps piling up on one particular side of it. To measure something as delicate as particle spin, buried deep inside a collision violent enough to briefly recreate the early universe, scientists needed instruments of almost unbelievable scale, cost, and precision, built to exacting tolerances. The Atlas detector, one of the two machines that confirmed entanglement, gives a sense of just how enormous this effort really is, a scale most people never picture when they hear the word laboratory. Atlas stands about as tall as a 7-story building and stretches roughly the length of half a football field. It weighs about as much as 100 fully loaded jumbo jets. It sits underground, built inside an enormous cavern excavated specifically to house it, surrounded by miles of tunnel connecting it to the rest of the collider, buried far below the fields and roads above. Inside this massive structure sit millions of individual sensors, layered carefully in concentric rings around the exact point where particle collisions happen. Each sensor is designed to detect a specific type of particle debris, flying outward from the crash, tracking its path, its energy, and its identity with extraordinary precision. When two protons collide at the center of Atlas, the resulting spray of particles can activate portions of this detector within a fraction of a billionth of a second. The sheer scale of data this produces is almost impossible to imagine using any kind of everyday comparison. The Large Hadron Collider can produce roughly 1 billion proton collisions every single second when running at full power. Atlas cannot record every single one in complete detail, so it uses an extremely fast filtering system, essentially a set of automatic decisions made in real time, to select only the most promising, potentially interesting collisions for full analysis, discarding the rest instantly. Even after this aggressive filtering, the amount of data collected over a single year of operation is enormous, far beyond what any team of humans could review by hand. This is why analyzing the entanglement signal required powerful computing systems working alongside physicists, sorting through roughly 1 million relevant top quark pair events extracted from a much larger ocean of recorded collisions. Building and operating a machine at this scale requires the coordinated effort of thousands of scientists, engineers, and technicians from countries all over the world. Nobody could build or run something like Atlas alone. It represents one of the largest cooperative scientific projects in human history, all aimed at answering questions too small and too subtle for any smaller experiment to reach. Questions that demanded this much scale just to get a clear answer. There is something worth pausing on here. Humanity built a structure the size of a cathedral, buried it underground, and used it to measure something as small and delicate as the hidden spin direction of a particle that exists for less than a trillionth of a second, That contrast between the size of the machine and the size of what it is trying to detect captures something important about modern physics. The deepest truths about reality often hide at scales so small that reaching them requires building something almost unimaginably large. As enormous as the current collider already is, scientists are still nowhere near finished pushing it even further. CERN has ongoing plans to upgrade the machine into what is called the High Luminosity Large Hadron Collider, a project designed to dramatically increase the number of collisions the machine can produce and record, essentially turning the current instrument into an even sharper tool. Luminosity, in this particular scientific context, refers simply to how many collisions happen within a given fixed amount of time. More luminosity means more data, more chances to catch rare events, and more statistical power behind every measurement scientists make. The current entanglement discovery, built from roughly 1 million top quark pairs, already required years of data collection and careful analysis. A higher luminosity collider could gather comparable amounts of data far more quickly, while also reaching rarer, more subtle events that current data simply does not contain enough examples of yet. This matters enormously for the mystery still left unsolved. The small amount of CP violation confirmed so far falls far short of explaining the full imbalance between matter and antimatter in the universe. Finding whatever additional source of asymmetry is still hiding will likely require detecting extremely rare particle decays, ones that occur so infrequently that current data simply has not captured enough examples to draw firm conclusions yet. More collisions mean more chances to catch these rare events in the act. The same applies to entanglement research. Confirming the deeper layers, quantum steering and full Bell non-locality, with the same overwhelming confidence already achieved for basic entanglement, will likely require even larger datasets than the ones currently available. A higher luminosity collider would give physicists exactly the kind of statistical power needed to settle these deeper questions with real certainty rather than early, promising hints. Beyond luminosity, physicists are also exploring proposals for entirely new colliders, some designed to reach even higher collision energies than the current machine allows. Higher energy means access to conditions even closer to the earliest moments after the Big Bang, and potentially the ability to directly create particles that current technology cannot produce at all, including hypothetical particles that could help explain dark matter or complete the picture of why matter outnumbers antimatter. These future projects take decades to plan, fund, and build. The current collider itself took years of construction before its first collision, and any successor would likely require a similarly enormous, sustained international effort spanning multiple generations of scientists. But the payoff from projects like these has historically been enormous. The current collider already delivered the discovery of the Higgs boson in 2012, along with the entanglement and antimatter results driving this very story. Every upgrade, every new machine, represents a bet that pushing further into extreme energy and extreme precision will keep revealing new cracks in our understanding of reality. So far, that bet has paid off consistently, again and again, for decades. Pushing further will almost certainly reveal something new. What that next discovery turns out to be is the only part still left to find out. Everything discussed so far in this particular story involves particles and effects that have already been fully confirmed. But some of the most exciting work happening around CERN right now involves searching for something that has never been detected at all. Particles predicted by theory but never actually observed in any experiment, anywhere, by anyone. Dark matter is by far the biggest, most famous example of this. Scientists know it exists, not because they have ever directly detected it, but because of how it affects everything around it. Galaxies rotate in ways that only make sense if far more mass is present than what we can actually see through telescopes. Roughly 85% of all matter in the universe appears to be this invisible substance, outweighing every star, planet, and visible object combined by a wide margin. Nobody knows exactly what dark matter is made of. One leading idea proposes an entirely new category of particle, one that barely interacts with ordinary matter at all, slipping through normal detectors almost completely undetected, like a ghost passing through walls. If particles like this exist, and if they can be created briefly inside high-energy collisions, they might occasionally leave behind an indirect signature, a gap in the data, or an unusual pattern of missing energy that current detectors could potentially catch. This is part of why entanglement research matters beyond its own strangeness. The same extremely precise measurement techniques developed to detect the subtle spin correlations in top quark pairs could potentially be adapted to search for other subtle, hard-to-detect signals hidden inside collision data, including possible hints of dark matter particles. There is also a broader theoretical framework called supersymmetry, which proposes that every known particle has a heavier partner particle that has not yet been discovered. If true, these partner particles could help explain several of the Standard Model's biggest gaps at once, including potentially explaining dark matter directly. Despite years of searching, the Large Hadron Collider has not yet found direct evidence for these predicted partner particles, which has led some physicists to reconsider or adjust the theory. While others continue searching at higher energy ranges, the collider has only recently become capable of reaching. This is simply how the frontier of physics actually works. Day to day, most searches for new particles do not immediately succeed. Scientists rule out possibility after possibility, narrowing down where a hidden particle could realistically be hiding, based on where it has already been proven not to exist. Each failed search is not wasted effort. It shrinks the map of remaining possibilities, making the next search more focused and more likely to succeed. One eliminated region at a time. The entanglement in antimatter results covered so far in this story are not searches for a brand new particle. They are confirmations of subtle effects predicted by existing theory. But the techniques, the precision, and the confidence built through these discoveries directly support the harder, more uncertain hunt still happening in the background. The search for something genuinely new, something that has never once been seen by human eyes or instruments. It is easy to treat discoveries like these as merely interesting but distant, locked away deep inside underground tunnels in Switzerland, with little real connection to daily life outside the narrow world of physics research. That reaction misses an important pattern that keeps repeating throughout scientific history, one worth remembering before dismissing a discovery as purely academic. Quantum mechanics itself, the entire framework that first predicted entanglement, sounded almost absurdly abstract and useless when it was originally developed in the early 20th century. Physicists debated it in university lecture halls, treating it largely as a strange, philosophical puzzle with little obvious practical use. Today, quantum mechanics quietly powers an enormous share of modern technology. Every smartphone camera, every laser, every piece of computer memory relies on principles first discovered by physicists arguing over whether particles could exist in multiple states at once. Entanglement specifically has already made the leap from pure theory into working, real-world technology. Quantum cryptography, a method of transmitting information so securely that eavesdropping becomes detectable the instant it happens, relies directly on entangled particles. Quantum computers, still an emerging technology, but advancing quickly, use entanglement to perform certain types of calculations far faster than any traditional computer. Calculations that could eventually transform fields like medicine, material science, and artificial intelligence. Confirming that entanglement survives at extreme, high-energy conditions expands the range of environments where these effects can be reliably studied and potentially used. Most current quantum technology relies on carefully isolated, extremely gentle laboratory conditions, because researchers assumed entanglement was too fragile to survive anything rougher. Proving that entanglement holds firm even inside violent particle collisions challenges that fragile reputation and opens questions about whether quantum effects might be more robust and more broadly usable than previously assumed, even outside a controlled lab. The antimatter research separately carries its own different kind of practical weight. Antimatter is already used today in a medical technology most people have heard of without realizing the connection, called PET scanning, a widely used imaging method that helps doctors detect cancer and study brain activity. PET scanners work by detecting positrons, the very same antimatter particles first discovered by Carl Anderson back in 1932, now used safely and routinely inside hospitals around the world. Improving our fundamental understanding of antimatter, including confirming exactly how it behaves under gravity, contributes to the broader scientific foundation supporting these existing technologies, even when a specific experiment is not designed with a direct application in mind. Basic research like this rarely arrives with an instruction manual explaining its future use. History shows, again and again, that the most abstract-sounding discoveries often become the quiet foundation underneath technology that feels completely ordinary decades later. Nobody at CERN can promise exactly what these specific discoveries will lead to years or decades from now. But the pattern connecting basic physics research to eventual real-world technology is one of the most consistent patterns in the entire history of science, repeating itself again and again across generation after generation of discoveries that once looked purely abstract and ended up changing everyday life. Some of the boldest, most daring ideas in modern physics take the entanglement results and push them into a completely different, far more speculative direction. One that touches on the deepest question a person could ever ask: what is space actually made of? Not what fills space, but what space itself is built from, underneath. For most of scientific history, physicists treated space as a fixed, empty backdrop, a kind of stage that objects and particles simply exist and move within, unchanging and always there. Even Einstein's general relativity, which showed that space can stretch, bend, and warp around massive objects, still treated space as a real, continuous fabric, something fundamental in its own right. A growing number of theoretical physicists around the world have started questioning that old assumption directly. Their proposal, still speculative and far from proven, suggests that space itself might not be fundamental at all. Instead, space could emerge from something deeper, a vast, underlying network of quantum entanglement connecting particles together. Under this view, distance between 2 points in space would not be a basic feature of reality. It would be a kind of measurement of how entangled two regions are with each other, with less entanglement corresponding to what we experience as greater distance. Picture an enormous, invisible web made entirely of connections similar to the entangled links CERN just confirmed between two top quarks, except stretched across the entire known universe, connecting countless particles together in an unimaginably complex pattern. Under this theory, what we experience as the three-dimensional space around us, up and down, left and right, near and far, would actually be something like a shadow cast by this deeper web of quantum connections, rather than a basic ingredient of reality itself. This idea remains genuinely unproven, and many physicists remain skeptical of it, or consider it one interesting possibility among several competing ideas trying to unify quantum mechanics with gravity. CERN's results do not confirm this theory. They simply confirm that entanglement is even more robust and widespread than previously proven, surviving in conditions nobody had successfully tested it in before. That robustness keeps this bold, speculative idea alive and worth continuing to investigate, rather than ruling it out early. If a theory like this were ever confirmed, the implications would reach far beyond physics research. It would mean the empty space surrounding you right now, the space between you and your screen, between the Earth and the Moon, between every galaxy in the visible universe, is not truly empty or fundamental at all. It would mean space itself is a kind of illusion, built from something far stranger underneath, an invisible web of quantum connection, linking everything together in ways we are only just beginning to detect and measure. one experiment at a time. Nobody claims to have proven this yet, but every experiment that confirms entanglement survives further and further into extreme, previously untested conditions, adds one more small piece of evidence to a puzzle that, if solved, would rewrite our most basic understanding of what the universe actually is. Underneath the space we assume is simply there. Every single previous test of entanglement before this particular experiment left open one nagging possibility. Perhaps entanglement was a delicate effect, one that only survived under gentle, carefully controlled conditions, and would naturally fade or disappear once energy levels rose high enough. Perhaps there existed some hidden threshold, an energy limit beyond which the strange quantum connection simply could not hold together anymore, snapping under enough pressure the way any ordinary connection eventually would. The top quark result challenges that entire assumption head-on. Top quarks are produced at energy levels far beyond anything used in earlier entanglement experiments, inside collisions violent enough to briefly recreate conditions from a fraction of a second after the Big Bang. If there was ever going to be a natural breaking point for entanglement, an energy level too extreme for the connection to survive, this experiment sat squarely inside the range where physicists expected it might finally show up. It simply did not show up. No matter how closely physicists looked, entanglement held firm, exactly as strongly as theory predicted, with no sign of weakening or fading at this dramatically higher energy scale. This raises a genuinely open, unresolved question that physicists are now taking very seriously. What if entanglement has no upper energy limit at all? What if this strange quantum connection remains just as strong no matter how extreme the conditions become, all the way up to energy scales far beyond what any collider on Earth could ever hope to reach? If true, this would mean entanglement is not a fragile, easily disrupted phenomenon confined to gentle laboratory conditions. It would mean quantum connection is a deeply fundamental feature of reality, one that persists through violence, heat, and energy levels that destroy almost everything else in its path. Few things in nature behave this consistently across such an enormous range of conditions, holding steady while everything around it gets torn apart. Physicists are now planning follow-up experiments specifically designed to push this question even further, searching for entanglement in other types of particle collisions at even higher energy levels than the top quark experiments reached. Each new confirmation narrows the possibility that some hidden limit exists, waiting just beyond the range currently being tested, still hiding somewhere further out. There is a genuine philosophical weight to this line of research beyond the pure physics involved. If entanglement truly has no breaking point, it suggests that the strange, connected nature of quantum reality is not some rare exception tucked away in careful laboratory conditions. It may be a constant, unbroken feature running underneath everything in the universe, at every energy scale, in every corner of existence, whether we have found a way to detect it yet or not. That possibility reframes the entire story. This may be evidence of a connection so deeply built into the structure of reality that no experiment humans can currently build is powerful enough to find its edge, if an edge even exists at all. Far bigger than a strange effect found once in one collider under one specific set of conditions. Pull every single thread of this story together, and a genuinely strange picture of reality starts to slowly take shape. One that goes far beyond any single experiment or any single discovery, stretching across every chapter of this story so far. Two particles born together inside a single violent collision do not carry a fixed, predetermined fate the moment they are created. Their connection remains undecided, flexible, right up until the exact instant someone measures one of them. At that moment, both particles' outcomes lock into place simultaneously, no matter how far apart they have traveled, with no signal, no delay, and no way to explain it using the comfortable common sense rules that describe almost everything else we experience. Meanwhile, an entire substance, antimatter, was created in nearly equal amounts to all the ordinary matter filling the universe today, and then almost completely destroyed itself moments after the universe began, leaving behind only a razor-thin margin of matter as the sole reason anything exists at all. That margin remains only partly explained, still one of the largest unanswered questions in modern science. And underneath both of these mysteries sits an even larger, more unsettling question. What if the very space separating objects, the very fabric that seems to keep two particles apart across a room, a planet, or a galaxy, is not fundamental at all, but instead emerges from an invisible web of quantum connections stretching across the entire universe? A web nobody can see, but everyone lives inside. None of this means reality is fake, or that nothing is truly real. An exaggeration that shows up constantly in casual conversation about quantum physics. It means something more careful, and, in its own way, more remarkable. At the deepest level science can currently reach, the universe does not appear to behave like a fixed stage, with predetermined props sitting in predetermined places, waiting patiently for us to walk in and observe them. It behaves more like something dynamic, something that stays genuinely undecided at its smallest scales, locking into a definite state only at the moment of interaction. Only at the moment something or someone actually looks, as if the universe waits to commit until it absolutely has to. Reality has always felt solid, dependable, and fixed, because at the scale of everyday human life, it overwhelmingly and consistently behaves that way. Tables do not flicker in and out of existence. The ground beneath your feet does not wait for you to check whether it is there before deciding to hold your weight. But underneath that solid, dependable surface, at the scale of individual particles inside CERN's collider, something far stranger and more flexible appears to be running the show, only becoming fixed and definite the moment reality is forced to reveal an answer. CERN did not break reality. It simply confirmed, with more precision and at higher energy than ever attempted before, that reality was never quite as fixed and solid as it feels from where we stand, and that the ground beneath the ground has always been stranger than it looked. There is a strange, persistent kind of tension sitting quietly at the center of this entire story, one worth naming clearly before reaching these final chapters. The standard model of particle physics keeps passing every test scientists throw at it. The entanglement result matched its predictions. The antimatter gravity result matched its predictions. Nearly every experiment run at CERN over the past several decades has confirmed rather than contradicted the existing framework of known physics. And yet every single physicist working on these experiments will tell you plainly that the standard model remains incomplete. It cannot explain dark matter. It cannot explain why gravity behaves so differently from the other fundamental forces. It cannot fully explain why matter outnumbers antimatter. These are not minor gaps tucked away in some obscure corner of the theory. They are enormous, fundamental blind spots sitting at the center of our current understanding of the universe. This creates an unusual situation in science. Physicists are simultaneously confirming that their existing theory works remarkably well, while also becoming more convinced than ever that a deeper, more complete theory must exist somewhere beyond it, waiting to be discovered. Every successful confirmation narrows down where that deeper theory could be hiding, without actually revealing what it looks like yet, like ruling out rooms in a house without ever finding the door. Think of it like exploring a large, mostly mapped forest, where every trail you walk down leads exactly where the map predicts. That should be reassuring. But you also know with complete certainty that entire unexplored regions exist just beyond the edge of the map. Regions the current map does not even attempt to describe. Confirming that the mapped areas are accurate does not tell you what lies beyond the edge. It only tells you that your map-making tools are trustworthy enough to eventually chart that unexplored territory correctly, once you finally reach it. This is exactly the position modern physics finds itself in today. CERN's tools, its detectors, its analysis methods, its ability to detect subtle effects like quantum entanglement inside violent collisions, have all been proven remarkably precise and trustworthy. That precision matters enormously, because the next major discovery in physics, whatever explains dark matter or gravity, or the missing antimatter, will likely require exactly this kind of extreme precision to detect and confirm. Some physicists compare this moment to the decades leading up to major past breakthroughs in physics history, periods where an existing theory kept getting confirmed again and again, right up until a single, unexpected result finally cracked it open and revealed an entirely new layer of reality underneath. Nobody can predict exactly when that next crack will appear, or what it will reveal, but the tools built to find it keep getting sharper. Every discovery covered in this story, the entangled quarks, the falling antimatter, the search for CP violation, represents another turn of that same sharpening process, pushing precision higher, ruling out wrong explanations faster, and narrowing the search for whatever waits just beyond the edge of the current map. Imagine, for just a moment, a collider even larger and far more powerful than the one already running today. Proposals for exactly this kind of machine already exist, some designed to dwarf the current 17-mile ring, stretching across even greater distances and reaching collision energies far beyond what current technology allows, opening a door into conditions no experiment has ever touched. If a machine like this is eventually built, one of the very first questions physicists would ask is whether these same strange results hold true at even higher energy levels. Does entanglement remain just as strong? Or does some hidden threshold finally appear, a limit nobody has been able to detect yet because current machines simply are not powerful enough to reach it? Does the small amount of confirmed CP violation grow larger and easier to detect at higher energy, finally revealing enough of an imbalance to fully explain why matter outnumbers antimatter? These are not small, minor, or incremental questions to ask lightly. The answers could reshape entire branches of physics. If entanglement genuinely has no upper limit, it would strongly support the idea that quantum connection is one of the most fundamental, unbreakable features of reality, present at every energy scale, everywhere, without exception. If a larger collider finally reveals a bigger, clearer source of CP violation, it could provide the missing piece needed to fully explain why the universe filled with matter, instead of annihilating itself completely at the very beginning. A future collider like this would take enormous time, funding, and international cooperation to build, likely spanning decades from initial planning to first collision, similar to the timeline that produced the current machine. These are not quick projects. They require sustained commitment across multiple generations of scientists, many of whom will spend their entire careers working toward a machine that will not produce meaningful results until long after the project first began. Despite the enormous cost and time involved, the scientific community continues pushing for these next-generation projects, precisely because the current collider has proven, again and again, that pushing into more extreme energy conditions reliably reveals genuinely new physics. The Higgs boson discovery in 2012, the entanglement confirmation in top quarks, the antimatter gravity results, each one emerged from pushing existing technology to its absolute limit, then building the next tool capable of pushing even further. There is no guarantee a future, larger collider would definitely solve dark matter, or fully explain the matter and antimatter imbalance, or reveal some entirely new category of particle nobody has predicted yet. Science does not offer guarantees like that, but the pattern connecting bigger, more powerful machines to genuinely new discoveries has held remarkably consistent for decades. And there is little reason, based on that pattern, to expect it will suddenly stop holding true. The next great discovery in physics may already be sitting inside data waiting to be collected by a machine that has not been built yet. Hiding at an energy level current technology simply cannot reach, quietly waiting for the next generation of scientists to arrive. Step back now, just for a moment, and take in everything this entire story has covered, from a wide distance, all at once. A machine 17 miles around, built underneath the border of two countries, smashing protons together hard enough to briefly recreate the conditions that existed a fraction of a second after the universe began. Inside that violence, scientists caught two of the heaviest particles ever discovered, sharing a single, undecided fate, locking into matching outcomes the instant either one was measured, with no signal, no delay, and no explanation that fits inside common sense, no matter how many times physicists tried to find one. In a separate facility, built from nothing but carefully shaped, invisible magnetic fields,